Hello there and welcome to the series of videos going through the content of A-Level Further Maths. Here we're looking at how we would find out how planes intersect using matrices and using the equations of those planes, so we can answer questions from exercise 6F. Now first of all, it'd probably be a good idea just to go over a brief overline of what a plane is. Now what a plane is, it's very similar to a line. So a line in 2D space, now this is 2 dimensions, obviously we only have an X and a Y dimension here. A line looks like this. Well, a plane is very similar but in 3 dimensions. We've got the Y variable going this way, the X variable going this way, and the Z variable comes effectively in and out of the page towards you and away from you. Now a plane is effectively then a sheet of paper or a 2D surface that exists inside of that 3-dimensional space here. So you can see here, I always think of it as a piece of paper looking in 3 dimensions. Okay, so this here is what a plane is. And what we're going to look at in this video is how they intersect with each other, the different possible combinations that they can intersect each other, and how we can tell this straight away from the equation of that plane. Now here, you could effectively say that, I'm just going to go over one more thing here, you could effectively say that we know that the coordinate 1, 2 goes through this line here, because when we plug in x equals 1 and y equals 4, we get an answer of 10. This plane here constitutes all of the 3D coordinates that follow this rule here. So for example, if we were to have the coordinate 1, 0, 2, that would fall on this plane here, because when we substitute in the coordinates of x is 2, y is 0, and z is 1, we get the value 10 at the end. So it's all of the set of coordinates that follow this rule here, where if you double the x coordinate, quadruple the y coordinate, and times the x z coordinate by 6, you get an answer of 10 when you add up these all together. Right, okay, let's now have a look at how we can tell whether or how these 3 planes may intersect each other. These equations here give equations of planes. Each of these is a different type of plane. It's the equation of a different sheet of paper in 3-dimensional space. And what we can quickly do from this is we can form a matrix. You can see here where the coefficients come from inside this matrix here. 1, 1, 1 along the top row, 2, 3, minus 1 along the middle row, 1, minus 2, 3 along the bottom row. So you can see where these coefficients in the matrices come from. And a quick way of telling whether planes are going to intersect or not, or all 3 will intersect together, is to have a look at the determinant. Now here we're checking out the determinant of this matrix here, and in this case here the determinant of the matrix is equal to minus 7. Because the matrix here is as a non-singular matrix, that means that we can solve this equation. A non-singular matrix means that the inverse exists, so therefore we can just invert this matrix onto the other side, just like we did in the previous video. If you haven't seen video part 1, then go and have a look at that. But what we could effectively do here is now find the one possible coordinate that all of these 3 planes will intersect at. And we can do that by applying inverse matrices to both sides of our equation here. We apply inverse A on this side, inverse A on this side. This is matrix A, obviously. That means these 2 will cancel out, leaving us just x, y, z. And apply inverse A on the other side as well. And do that mostly on your calculator, and you'll get the single coordinate at which all 3 planes intersect. X equals 1, y equals 3, z equals minus 2. And if you were to substitute those coordinates into all 3 equations, you'll see that they would all work. They would all come out to equal the correct number at the end, 2, 13 or minus 11. So this here is the single coordinate at which the 3 planes here would intersect. We knew it had 1 intersection point because the determinant of the matrix was not 0, it was a non-singular matrix. So what you'll have here is them all intersecting at one point. I think it looks like it's this point here. We've used a graph plotter here. You're certainly not expected to be able to draw the equations of planes. You're certainly not expected to do that. But just a little bit of a heads up, when you have a non-singular matrix, that means that you get one solution where the x, y, and the z coordinates will all intersect at one point, or all of the planes will intersect at one point for x, y, and z. Okay, now that's the case of when the matrix is non-singular. We are now going to look at the other cases, and there are lots of more cases here in which the matrix is singular, because when it's not singular, when it is singular, we get lots of different things happening, but all three of the planes will not intersect at one point. So when the determinant is not equal to 0 or non-singular, just like we've shown in this example here before us, we get one point of intersection. But when the determinant is equal to 0, lots of things could happen. We could have all three of the planes overlap each other and effectively form the same plane, just in different ways. It's effectively the same as you can represent the line of the equation of a line in different ways. So we could see here that the three planes may just be represented in different ways. So that's one possibility if the determinant equals 0. Another possibility is that we could have some parallel planes. Remember that you can have parallel lines where you can also have parallel planes, or you could have two planes that are parallel and one plane that intersects them. You can see in this case here that all three planes, the blue, the red, and the green here, won't intersect each other all at the same time. We could have them all intersecting each other but along a line. So along a line, so there's not one clear solution here. In this case here, there was one single solution. One single solution. But in all these cases below here, there is not one single solution. And the final option that could appear here is this kind of strange looking prism here, where the planes are parallel in one dimension, or in one direction, that form then a triangle going through the planes there. So how can we tell, given the equations, what happens given our equations? Let's go through this example here where all of the planes overlap at once. How can we tell from these three equations that this is going to happen? How can we go from this to knowing that this will happen? Well, from just observation, we can see that each of the planes is effectively a scale factor multiplier of each other. The first one to the second one, you just have to multiply by 2 all the way along. And from the first one to the third one, you can see that it's just a scale factor of -1. So effectively, it's the same plane, just with a scale factor multiplier there. Effectively, you could think of it as the same as y equals 3x. Could be written as 2y equals 6x as a line, if just looking at the equation of a line in two-dimensional space. They're effectively the same equation. One would, if you were to draw it on a graph plotter, you'd have one graph appearing above the other. Okay, so in this case here, it should be clearly observable that one or all three of the equations are scale factor multipliers of another. In this case here, where we have either 2 or 3 parallel planes, the way that we spot a parallel plane, if we look at just the first two equations here, is that the coefficients are scale factors of each other, but the number at the end is not a scale factor, or the same scale factor as the variables before. It's effectively the same as if you were doing y equals 2x plus 5 and 2y equals 4x plus 7. You'll have a scale factor multiplier on your lines here, but not on the coefficient at the end, which means that these planes here would be parallel. Okay, these planes here are parallel, so we can tell that it's not going to intersect at any point. If planes are parallel, it's effectively a sheet of paper travelling in the same direction as another sheet of paper. This equation at the end here, it's not observable that there's any clear scale factor from either equation 1 or equation 2 to equation 3. So in this specific case here, it's going to be this type of equation here, this type of plane construction here, where we have 2 parallel and 1 not parallel. The coefficients on the third plane are not multiples, so this plane contains 2 parallel planes and 1 intersecting. Let's just go back to this one here. If, for example, this plane here was not that equation there, and it had the equation 3x plus 3y plus 3z equals, let's give me some random number, 17, then it would be this case here. We'd have equation 1 would be a scale factor multiple of 3 onto the third equation, but not the number at the end. If this is not the same scale factor at the end, then it means they're parallel. If it is the same scale factor at the end, it means they're exactly the same. They lie one on top of another. In this case, they're not the same, so they're just parallel. Now it gets a little bit more difficult. We're going to look at 2 different examples here where we have to do a little bit more thinking to this. How can we tell from these 3 planes here that this is the construction of the planes when we plot them? How can we tell that it's going to lie, they're going to have infinitely many solutions along a line? The way that the example would want you to label this is by a sheaf. It effectively forms a nice flowery pattern. How can we tell from these 3 equations? Well, what we do is, first of all, what I would do first is check the determinant 0. The determinant in this case is going to be 0, and the strategy that we're going to follow, given that we've found that the determinant is 0, is we're going to attempt to solve the equations using elimination of one variable in 2 different ways. Let me show you how we're going to do that. Call them equations 1, 2 and 3, or A, B, C, or star, double star and triple star, however you want to label them. And we're going to look at cancelling out one of the variables in a different way. In this case here, I think it looks like we're going to cancel out the z variable here. We can see that we're doing equation 1, add 2 lots of equation 2. So that's going to give us a 6z here. That will cancel out with the negative 6z here when we add the equations together. So it's going to be 3x add 2x, because we're doubling the second equation, 5x. It's going to be minus y add 6y, that's going to give us 5y because we double the second equation. The z's drop out and it's going to be 1 add 4 because we double the second equation. Let's now try and cancel out z in a different way. Let's do equation 2 take away equation 3 because they're both 3z's, so let's just subtract one equation from another. So x minus 3x gives me 4x because it will be x minus 3x. There will be a negative from subtracting the equations and a negative from the coefficients. That will be a double negative to make 4x. 3y take away minus y will give me 4y, and 2 take away minus 2 will give me 4. And what do you spot from these 2 equations that we get here? We have 2 equations that are identical, or a scale factor multiple away from each other. So therefore, as the equations are identical, the plane construction here is going to have infinitely many solutions along this line here. Okay, so this results here, the fact that the 2 equations are identical, means that it looks like this. It means that within this equation here there are going to be infinitely many solutions that satisfy both of these equations here, so effectively therefore there are then infinitely many solutions along this line here. This effectively is what it looks like. So you can see down here, down that line there of intersection, that's where there are infinitely many solutions. Alright, let's now have a look at how we can tell that the planes form this type of construction here. So these are our planes. How can we tell that these three planes make this shape here? Well, we apply the same steps that we did previously. We attempt to solve the equations in two different ways. We're going to attempt now to cancel out one of the variables in two different ways. This time here, I think we're going to look to cancel out the x variable. Now, it doesn't matter what variable you cancel out. It could have been the y variable, it could have been the z variable. In this case, we're going to cancel out the x variable. 3x and minus 3x, those two will cancel when we add the equations together. So we're going to get 6y add minus y, that's 5y, minus 6z add 3z, that's minus 3z, minus 6 add minus 2, that's minus 8. Let's see if we can cancel out the x variable in another way. This time we're going to double the first equation and add it on to the second equation here. So that will make this 6x, add that onto minus 6x and now cancel out. So it's going to be 12y add 3y, that's 15y, minus 12z add 3z, that's minus 9z, and minus 12 add 2 gives me minus 10. Now what do we notice from these equations? We notice from these equations here that they are almost identical. We have a scale factor multiplication from the coefficients on the y and the z, but the number at the end does not work with the same scale factor. Okay, so in this case here, what we have are parallel lines. 5y minus 3z equals minus 8 and 15y minus 9z equals minus 10. They are two parallel planes, which makes sense because these planes here are going to have to kind of be parallel, certainly in one dimension anyway, to form the triangular prism that this shape gives us. So we can see here that because our two equations came out here as parallel and not identical, that means here that we don't get infinitely many solutions along a line, we get no solutions along a line that effectively gives us then a triangular prism. Okay, so these three planes here form a prism, and this is what it would look like if you plot it on a diagram. Right, so what does your train of thoughts need to be as you work through these types of problems here? First of all, before you start doing anything, check whether the determinant equals 0, because if it isn't, if the determinant is something like a 7 or a 9 or a minus 2 or a 1/2, you know that you can solve those three planes. You know that there is one intersection inside those three planes where all three planes will intersect and only one solution. The reason being is if the determinant is not equal to 0, the matrix then has an inverse, and then we can solve that equation. Feel free to start the video again to see that problem play out. If the determinant is 0, then what you've got to do is a little bit of an inspection first to check whether you've noticed something. You can notice a couple of different things, whether all of the planes are identical, or whether you have some parallel planes. Remember, you can spot identical planes because there should be one constant scale factor between one equation and another, and then maybe a different scale factor to get from one equation to the third equation. Or maybe you've spotted some parallel planes. Maybe there's a scale factor in the coefficients but not the number at the end. Does that happen to all three planes, or does it happen to just two planes and then one other random plane that may intersect them? If you haven't noticed anything about the planes, or there's nothing to spot, either scale factors inside those planes, then what you've got to do is the long method of trying to solve the equations, eliminating one variable in two different ways. And what do you spot with your two equations that you get afterwards? Are your two equations identical? Is there a common scale factor between all three values? If there is, then it has an infinitely many intersections along a point. If it doesn't, and you form two parallel equations, in other words, the coefficients have a scale factor but the number at the end doesn't, then you form a triangular prism. This is a triangular prism, this is a sheaf. These are identical planes, these are parallel planes. Okay, so another word that I want to introduce is the word consistent. Now, if an equation is consistent, then it has some points, either one or more points, at which the equations or the planes intersect. That diagram there is consistent. This diagram here is consistent because there is more than one point at which all three planes intersect. These planes here are not consistent. These planes here are consistent because there is more than one point at which all three planes intersect. And this plane construction here is not consistent because there is not a single point at which all three planes intersect. Okay, so that's all we have time to go through in this video here. I don't want to go through any more problems because I want to leave as many questions for you as possible to answer from the textbook. So if you need to, go through the problems again and see if you can do them without the video instructing you what to do, or have a go at some more of the exercises from exercise 6F. So yeah, have plenty of practice, make sure you've got it nailed, and yeah, thanks very much for watching.